Today we're gonna learn something about simple harmonic motion. This is a chapter in physics, 11th physics. We're gonna learn something about that. So let's start with periodic motion. Periodic motion. Periodic motion is a sort of motion which gets repeated over the period of time, and the fixed interval of time or the fixed time period, fixed time, that is called as time period. Okay, time period. That means the motion gets repeated over the period of time, and that fixed time, we call that fixed time as time period. And suppose the earth moves around the sun, and the time period for that motion, time period for the rotation of earth around the sun is approximately a year. That equals 365 days. And for time period for the motion of hour's hand in a clock, that is 24 hours. And for a seconds pendulum, it is approximately 1 second. So this is whole about periodic motion. And after understanding periodic motion, let's turn to oscillatory motion. Oscillatory motion. Oscillatory motion is actually a sort of motion in which a body moves towards or backwards. That means body, when we apply force on a body, the body may move in a forward direction or in a backward direction. It's actually a sort of periodic motion because the time period for this motion is also fixed, and that's also what we call time period. And every oscillatory motion you study is periodic because the time period remains same in both the cases, both in periodic motion as well as oscillatory motion. But every periodic motion is not oscillatory motion, because it's not important that in every periodic motion there will be the fixed time, there will be a time period. Okay, so this is all about oscillatory motion. And taking an example of oscillatory motion, you can look about this pen. Look at this pen. So when I apply force on this marker, you will see this marker you will firstly move in this direction, and after that, after reaching to this point, this will also move in this direction. So you can see the marker is moving in firstly it moves in a forward direction, then in a backward direction. So we can call this type of motion as oscillatory motion. And also you can see motion of a pendulum. If you see in a the pendulum which you must have seen in watch, that in that case in clocks, in that case you can see also that's also a case of oscillatory motion. So this was all about periodic motion and oscillatory motion. So what is the crux of this oscillatory motion is that in this type of motion there is a sort of motion which includes to and fro. Okay, so this was about oscillatory motion. Now let's move towards harmonic motion. Harmonic motion. Harmonic motion is a sort of motion which can be represented by harmonic functions. That means it's actually a sort of oscillatory motion. If it's an oscillatory motion, then there must be a to and fro motion, and if it is an oscillatory motion, then it must be a periodic motion in which the time period is fixed. So in harmonic motion is a sort of oscillatory motion, but in this type of oscillatory motion, in this type of oscillatory motion, the harmonic motion is represented by the harmonic functions. And you must know what actually a harmonic function is. Harmonic functions are sine and cosine. Sine and cosine are the harmonic functions. So this was about periodic motion, oscillatory motion, harmonic motion. Now let's move towards simple harmonic motion, which is actually our topic. Simple harmonic motion. Simple harmonic motion, it's actually our topic. Simple harmonic motion, it's actually the topic through which we have to go. So simple harmonic motion. In simple harmonic motion, there is constant amplitude and constant frequency. So simple harmonic motion is a sort of harmonic motion in which amplitude and frequency remains constant. And let's look at this marker. If I apply a force on this marker, this will move in this direction, and when it comes back, when I keep this, I just apply force on this marker, it will come back to its mean position, and after attaining the mean position, it will move in this direction as well, because it has attained a sort of inertia. By applying force on this direction, it gains a restoring force, and that restoring force is in the opposite direction, and that's why in simple harmonic motion this restoring force comes into play, and this restoring force is actually inversely proportional to x, and this x is actually the displacement. This x is actually the displacement through which we have displaced this marker. And what is the significance of this minus? This minus signifies that the force which just came into play is in the opposite direction of that force that we have applied. It's in opposite direction of that. So this is one of the important points that you learn in simple harmonic motion, that the restoring force is directly proportional to the minus of displacement. Okay, so if I remove this proportionality constant, I will write like this: F is equal to minus kx, and this k is the proportionality constant. Okay, and this can also be called as force constant. Force constant. And in simple harmonic motion, to know whether a motion is simple harmonic motion or not, what we have to do, we have to find that if force is proportional to minus of x, or if acceleration is proportional to minus of x. If we find any of these conditions, we will understand that the motion is a sort of simple harmonic motion, or simply we can say the motion is simple harmonic motion. Now let's see how can this simple harmonic motion be represented. How can we represent this simple harmonic motion? Equations representing simple harmonic motion. What are the equations through which we can say that the motion is simple harmonic? One of the first form that we have to go through is sine and cosine form. Sine and cosine form, like y is equal to a sine of omega t, or x is equal to a cos of omega t. If you find y as y equals a sine of omega t, or x equals a cos of omega t, then that is actually the equation. That's actually the equation for the displacement of a body executing simple harmonic motion. So this is one of the forms, and the other form can be sine or cosine, or sine or cosine form with phase angle. This is the another form for the displacement of a particle executing simple harmonic motion. So this can be written as y is equal to a sine of omega t plus y is equal to a sine of omega t plus minus phi, or x is equal to a cos of omega t plus minus phi. Okay, y is equal to a sine of omega t plus minus phi, x is equal to a cos of omega t plus minus phi. So this was the second representation of equation of a particle executing simple harmonic motion. And the other form is complex form. Complex form. Complex form is y equal to a sine of omega t plus b cos of omega t. This is the complex form of a this is a complex form of an equation. That equation represents the displacement for the particle executing simple harmonic motion. So this can also be written as y is equal to a capital A sine of omega t plus minus phi. So these two are unknown over here. So this a is actually equal to under root of a square plus b square, and this phi is actually equal to tan inverse of b by a. So if you are given an equation in this form, you are given y is equal to small a sine of omega t plus b cos of omega t small b. So you can find an equation, you can convert a equation given in complex form to an equation given in simpler form. You can convert it from complex form to simple form by just finding a capital and phi. A can be found by this equation, a equals under root of a square plus b square, and phi can be found by using this equation, phi equals tan inverse of b by a. So these were the equations representing the simple harmonic motion, or the equations representing the displacement for a particle executing simple harmonic motion. So let's now look at the other forms that are actually the oscillatory forms, periodic forms, but those forms are not simple harmonic motion. Those forms of equations don't represent actually the simple harmonic motion. So now we will see equations not representing SHM. So what are the equations? If we look at some equations, we are given some equation and we have to find whether the particle is executing simple harmonic motion or not. So those forms are like this. If we are given y equal to a sine of omega t plus b sine of twice omega t dash 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 dash. So if we are given y is equal to a sine of omega t plus b equal to plus b sine of twice omega t dash dash dash, so on and so forth. If we are given an equation like this, this equation does not represent the simple harmonic motion. Why it does not represent the simple harmonic motion? Because you can see here the frequency is omega and here the frequency is 2 omega. So if we move on, the frequency keeps on changing, it increases. So we can't say that we cannot call this equation as equation that represents simple harmonic motion, because here the frequency of the particle changes. So we cannot call this if we cannot call this equation the equation which represents simple harmonic motion, because here the frequency changes, and we have already learned that in simple harmonic motion the frequency should remain angular frequency, or the angular frequency should remain constant. So here you can see that does not remain constant, the frequency does not remain constant, so it's not the equation which represents simple harmonic motion. So the other form is, if we are given sine y equal to sine square of omega t, or x is equal to cos square of omega t, y is equal to a sine square of omega t, or x is equal to a cos square of omega t. These two equations also don't represent the simple harmonic motion. So let's move on to the other topic, that is how to find the equation of a particle, equation for the displacement of a particle executing simple harmonic motion. Equation for displacement. Equation for displacement. Equation for displacement. Actually the projection, just a minute, this x-axis, this is y-axis, and this is a circle. The motion of a particle executing simple harmonic motion can be represented by the motion of a circle in a circular path. This we are given. Let us suppose here is a particle P whose coordinates are x comma y, and this is the maximum distance of a particle from the mean position, that is a, and the x component of the particle, that's x, and the y component of the particle, that's y, and this the particle makes an angle of the line which connects the particle to the mean point, that cuts an angle of theta with the x-axis. And now, as we know, this a can be also written as, this a can be also given as the x component of a, that is equal to a cos of omega t, and the y component of a, that's equal to a sine of omega t. So here you can see x is equal to a sine of omega t, and y is equal to a cos of omega t. Now you must be thinking why I have written omega t, because here is theta, because as you know, omega is equal to theta divided by t, and theta is equal to omega t. So actually this was x is equal to a sine of theta, and y equal to a cos of theta. So I have just, what I have done, I have just replaced this theta by omega t. So these are the equations. This is actually the derivation for the equation of displacement of a particle executing simple harmonic motion. This is actually the derivation. Now let's move on to the other topic, that is, now you know that if a particle executes simple harmonic motion, its equation for displacement is given by y is equal to a sine of omega t, and we write this equation if the particle starts its motion from the mean position, and if the particle starts its motion from the rest or from the extreme position, then we write y equal to a y equal to a cos of omega t. So if a particle starts its motion from the mean position, then we write y is equal to a sine of omega t, and if a particle starts its motion from the extreme position, then we write y equal to a cos of omega t. Okay, now these are the two equations representing simple harmonic motion. These are the equations of displacement of a particle executing simple harmonic motion. So now we have to find the equation for the velocity of a particle. Now we have to derive actually the equation for the velocity of a particle executing simple harmonic motion. Equation for velocity. So as you know, velocity is actually the rate of change of displacement. So we can just calculate velocity by simply differentiating the equation of displacement. Velocity equals dy by dt. So d by dt of a sine of omega t. So this will come out to be a cos of omega t into internal differentiation of sine of omega t that equals cos of omega t, and internal differentiation of omega t that equals omega. So equation for the velocity of a particle executing simple harmonic motion will be given by a omega cos of omega t. This is the equation for the displacement of a particle executing simple harmonic motion. So we are given this equation in the form of in harmonic form. So you can also write this equation of velocity in displacement form in other form. So simply what we will just replace this cos of omega t. So how will we do this? We will just write, as we know, sine square of omega t plus cos square of omega t is equal to 1. So cos of omega t will be equal to under root of 1 minus sine square of omega t. So we can replace this cos omega t by under root of 1 minus sine square of omega t. So this will be v equal to a omega under root of 1 minus sine square of omega t. As we know, sine of a sine of omega t is equal to y. So sine of omega t will be equal to y by a. So we can write here v is equal to a omega under root of 1 minus y by a square. So after simplifying this will come out to be v is equal to omega under root of a square minus y square. So this is actually the relation between the velocity of a particle and displacement of a particle executing simple harmonic motion. So till now about the velocity, we have learned that velocity of a particle executing simple harmonic motion is equal to v is given by v equal to a omega cos of omega t, and it can also be written as v is equal to omega under root of a square minus y square. Now there are other important cases of this velocity which we will discuss. As we have already learned that v is equal to omega under root of a square minus y square. So this is the equation we're gonna use. Now let's see what is the value of velocity at the mean position. At mean position. as you know, when the body is at mean position, let us suppose if I consider this body, when it is at mean position, its displacement is actually equal to 0. So we're gonna take here y equal to 0. So what is the value of velocity? V will be equal to omega under root of a square minus y square. Y equal to 0, a square minus 0 square. That will be omega into under root of a square. Root square cancel, that will be equal to a omega. So value of velocity will be equal to a omega, and it's actually the maximum value of velocity. So the maximum value of velocity is actually at the mean position. So what is the maximum value of velocity? That's equal to a omega. We can also write that v max is equal to a omega. That means the maximum value of velocity is actually at the mean position, and that equals a omega. Now at extreme position, now let's find the value of the velocity at extreme position. What is the actual value of velocity of a particle which executes simple harmonic motion at the extreme position? So this means when I apply a force on this marker, this will go to this extreme position. So when I apply force on this marker, this will go to this extreme position, and the displacement for this extreme position is actually equal to amplitude, and the amplitude actually is the maximum displacement of a particle. So here y will be taken as y equal to a. So we will write as v equal to omega under root of a square minus a square. So the velocity will come out to be 0, and it is actually the minimum velocity. So at extreme position, the velocity of the particle is actually 0. So it means at extreme position the value of velocity is 0, and we take y equal to a. That's actually the maximum displacement. So when the displacement is maximum, velocity is minimum. When the displacement is minimum, velocity is maximum. And the velocity is maximum at mean position, and it's minimum at extreme position. Now let us see what's the value of velocity at half amplitude. Half amplitude means y equal to a by 2. By using the same formula as we have used above in these cases, velocity will actually come out to be under root of 3 divided by 2 a omega. At half amplitude, at y equal to a divided by 2, velocity is given by under root of 3 divided by 2 a omega. As we also know that this a omega is actually equal to the v max, maximum velocity. So we can simply write here that velocity at half amplitude is given by under root of 3 by 2 v max. So this was all about velocity. So now let's move on to acceleration. How we can calculate the acceleration of a particle executing simple harmonic motion. Acceleration. As we know, acceleration is actually the rate of change of velocity. So acceleration will be given by dv by dt. As we already know, d by dt, velocity is equal to a omega cos of omega t. That will be, a will be equal to d by dt of a omega cos of omega t. and this will actually come out to be a, taking these constant out of the differential, and this will be equal to minus sine of omega t, internal differentiation of omega t, that equals omega. So acceleration will be minus times a omega square sine of omega t, that will be equal to minus times omega square a sine of omega t. But this a sine of omega t, this is actually equal to y, so we can simply replace this a sine of omega t by writing here a equal to minus omega square y. So this is the expression for the acceleration of a particle executing simple harmonic motion, and is given by a equal to minus times omega square y, or this can also be written as a equal to minus kept amplitude times omega square sine of omega t. This is the in harmonic form, in sine form, and this is in displacement form. So let us see where the acceleration of the particle is maximum and where the acceleration of a particle is minimum. So let's see first at mean position. At mean position, as we all know, when we talk about mean position, y should be equal to 0. So the acceleration will be minus times omega square 0, that will be equal to 0. So the acceleration will be minimum at mean position, and that will be equal to 0. So the acceleration for the particle is minimum at mean position, and that is equal to 0. Now at extreme position, as we know, when we talk about extreme position, y is equal to a. When we talk about extreme position, we take y equal to a. At extreme position, a will be maximum and will be given as minus times omega square. We write a in place of y, and the maximum acceleration will be minus times omega square a. So this is all about acceleration, and acceleration is actually the rate of change of velocity, and we have written acceleration actually in two forms. Y is in the sine form, and in sine form we write a equal to minus times omega square a sine of omega t, or simply in displacement form we write acceleration equal to minus times omega square y. And at mean position, when we take y equal to 0, the acceleration is minimum and it comes out to be 0. And at extreme position, when y is equal to a, acceleration is maximum and it comes out to be minus times omega square a. Thank you. This was all about the motion of a particle executing simple harmonic motion. Later we will learn about the kinetic energy, what happens with the kinetic energy, what happens with the potential energy, and the other aspects of this topic, simple harmonic motion. Thank you.